Jai Hind everyone. I am Krishna Gupta. I am assistant professor in Electronics and Communication Engineering Department in Ajay Kumar Garg Engineering College. This is lecture 4 of the subject Integrated Circuits. In this class, I am going to discuss CMOS realization of Boolean expressions. Right. So, as far as CMOS is concerned, so it is very much used because in today's era, most of the ICs are CMOS based. Fine. There are various advantages of CMOS, that's why we are very much interested in CMOS. So, in this class, I am just going to discuss few examples, few Boolean expressions. I will take few Boolean expressions and will discuss that how we can draw the CMOS circuit of those Boolean expressions. Because once we understand, then we can apply these concepts to various other digital circuits, combinational as well as sequential. So, mainly I will discuss the examples of the Boolean expressions and we will implement Boolean expressions using CMOS. So, firstly starting with some basics. As far as this CMOS inverter is concerned, CMOS, that stands for complementary metal oxide semiconductor. It is called complementary because at a time only one transistor is on, another one is off, and it consists of two transistors, PMOS and NMOS. So, as far as PMOS is concerned, the source of the PMOS is connected to the higher potential and the source of NMOS is connected to the lower potential. Let's say it is ground, and upper transistor, let's say this is M2 transistor and the lower one is M1, and this M1 transistor is NMOS. M2 transistor is PMOS. You can see that the arrow at the source is inwards, that is PMOS, and the arrow at the source is outwards, that is NMOS. And the source of the NMOS is at lower potential and the source of the PMOS is at higher potential, that is the supply voltage VDD. So, in CMOS inverter, we apply the input at the gate of both the transistors, that is NMOS and PMOS, that is Vin, and we take the output V0 from the drain of two transistors NMOS and PMOS. So, this is the basic CMOS inverter. It is inverter circuit because if input is low, then output will be high, because if input is low, then PMOS will be on. So, output will go to the higher node voltage. So, output will be at high. Similarly, if Vin is high, then NMOS will be on. So, output will go at the lower voltage side. So, output will be low. So, for logic 1 input, we are getting logic 0 and vice versa. That is why it is called inverter, and it is CMOS because we are using this NMOS and PMOS transistors in this arrangement. Fine. So, this is the basic CMOS inverter. Fine. And you can see that we have applied only one input V, but in order to implement different Boolean expressions, there can be more inputs. There may be 2 inputs, 3 inputs, 4 inputs, 5 inputs, n inputs. There may be n inputs. So, how we will draw the CMOS structure of those Boolean expressions? Before that, let us quickly cover why we are so much interested in CMOS. Because there are various advantages of CMOS. One of the advantages is its steady state power dissipation is very less. Steady state power dissipation is very less because there is no direct path from VDD to ground. That is one of the most important advantage of CMOS inverter. Another advantage of CMOS inverter is the voltage transfer characteristics, that in short we say VTC, voltage transfer characteristics. It is sharp and it is close to the ideal inverter VTC. That is another advantage. And also noise margin of CMOS inverter is high. So, these are the few main advantages of CMOS inverter. That is why we are very much interested in CMOS. That is why we want to know the CMOS structure of various digital circuits. Fine. Now, if I draw the general structure of CMOS for any Boolean algebra, then we can imagine that there will be two kind of networks. One network will consist of NMOS transistors and another will consist of PMOS transistors. The NMOS transistor network, it will be referred as pull down network, because you can see that if NMOS transistor is on, then output voltage it will go at the lower side, pull down, and if the PMOS is on, upper transistor, then output will go to the higher voltage side. That's why this pull up network consists of PMOS transistors and pull down network consists of NMOS transistors. So if I draw this network, so one is pull up network that consists of PMOS transistor, and the another one is pull down network that consists of NMOS transistors. If we take 3 input circuit, let's say these inputs are A, B, C. So these 3 inputs, it will also be applied at NMOS transistors at pull down network also. The source of pull up network, that is that will be connected to VDD, and this one is ground. From drain we take the output V0, or we can say the output expression, that is Y. Anything we can take, that is just the notation. So this pull up and pull down, when we combine this pull up and pull down network, overall structure is called CMOS structure, and this pull up, that is PMOS transistor, and pull down, that is NMOS transistors. That is the general structure of CMOS logic circuits. Now see, firstly we need to understand that in pull down network, when we take these NMOS transistors, then how we will connect those NMOS transistors, whether it will be connected in series or parallel. Similarly, when we take pull up network, that is PMOS, so how we are going to connect those PMOS transistors, in series or in parallel? So there can be 4 cases, like NMOS transistors are in series and parallel, 2 cases. PMOS transistors are in series and parallel, another 2 cases, total 4 cases. So from there we can understand that when it will be connected in series and when it will be connected in parallel. So if I take the first case where 2 NMOS transistors are in series, it means that we are taking 2 input circuit, right? If there are 2 inputs, then 2 NMOS transistors will be required, and further 2 PMOS transistors will also be required. If we are taking 3 input circuit, then 3 NMOS and 3 PMOS, 4 input, 4 NMOS and 4 PMOS, fine. So if we are taking 2 input circuits, so 2 NMOS and 2 PMOS, total 4 transistors. So if the inputs are A and B, and let's say these transistors are M1 and M2, and M1 and M2 are NMOS, and this dotted line, what it is showing, this dotted line is showing that the upper network is the pull up network, right? And from here we are taking the output Y. Now what will be Y? See, the output node Y, it will go down only when both the transistors M1 and M2 are on, and M1 and M2 transistors will be on when A and B both are logic 1, because if A and B both are logic 1, only then both the transistors will be on, because these are NMOS, and only then output will go down. It means that both are important, so we can write it as A dot B, and output will go down, so we can represent it as Y bar. So what will be the value of Y here? It will be A dot B whole bar, A dot B whole bar. So it means that if there is a dot operation with inversion, then NMOS transistors will be connected in series, and when NMOS transistors are in parallel, that is the case 2. Similarly, you can find out when NMOS transistors will be in parallel, then this expression Y bar, this Y bar will be equal to A plus B. So y will be equal to a plus b whole bar. So it means that if there is a OR operation with the bar, then NMOS will be in parallel. And one more thing about pull up and pull down network. If NMOS transistors are in series, then PMOS transistors will be in parallel. And if NMOS transistors are in parallel, then PMOS transistors will be in series. Just opposite, series, parallel, parallel, series. So how this series parallel comes? You can find out. Just I have given one case, one example, case 1. Similarly, you can just connect two PMOS transistors in series and PMOS transistor in parallel. From there, you can easily find out that when we need to convert, when we need to connect PMOS transistors in series, when we need to connect PMOS transistors in parallel. Fine. Now, coming to the example part. So the first example is, let's take y is the output and y is equal to AB plus CD whole bar. Now see, this series parallel, it is working when there is a whole bar. If there is not whole bar in the expression, for that we need to connect one more CMOS inverter at the output, because you can see that from case 1 you can see that y is equal to a dot b bar. If there is a dot operation but there is a bar also, only then these two NMOS transistors are in series. So while drawing the CMOS circuit of any Boolean expression, first see that whether there is a whole bar or not. If there is no whole bar, then there are two methods. The first method is just take double bar and just solve it using De Morgan's theorem. That is one approach. Another approach is, if there is no overall bar in the expression, then just draw the circuit and just connect the CMOS inverter at the output side. But that is important, right? So from here you can see that AB plus CD, A, B, C, D are the input variables, inputs. So there are 4 inputs, A, B, C, D. So there will be 4 NMOS transistors required and 4 PMOS transistors. Now you can see A dot B, dot operation. It means that 2 NMOS transistors whose inputs are A and B will be in series. And C dot E, it means that 2 NMOS transistors whose inputs are C and D will be in series. And both the sections will be in parallel because there is a this OR operation also. Fine. So once we draw the pull down network, we can easily draw the pull up network, just interchanging the series and parallel. Fine. So firstly, I am just going to draw the pull down network that will consist of NMOS transistor. So see, A dot B, it means that 2 NMOS transistors. Let's say these NMOS transistors are M1 and M2, and obviously the inputs will be A and B, right? A and B dot operation. So M1 and M2 are in series. Similarly, C into D. So another 2 NMOS transistors, that is M3 and M4. This is M3 and M4, and the inputs of M3 and M4 are C and D. Fine. Now this AB and CD both are added, so there is a OR operation, means both the sections will be in parallel. Both the sections will be in parallel, and the source of the NMOS, it will be connected to ground. So up to now I have drawn the pull down network. Now coming to the pull up network, that will consist of PMOS transistors. Now whatever, if there is series connection in pull down network, then there will be parallel connection in pull up network. Just go step by step. So M1 and M2 transistors, NMOS transistors, M1 and M2 NMOS transistors are in series. So equivalent to it, and we will take 2 PMOS transistors and these two PMOS transistors, it will be in parallel, and the inputs of these two PMOS transistors, let's say this is M5 and M6, the inputs will be same, inputs will be A and B, and this M5 and M6, it will be in parallel, fine. Now you can see that M1 and M2 transistors, it is having two inputs A and B, but in pull up, A and B input transistors are in parallel, right? Similarly, we will require two more PMOS transistors at which the same input will go, that is C and D. So C and D inputs, that is coming at the gate of M3 and M4, and M3 and M4 are in series. So those two PMOS transistors, that will be, let's say M7 and M8, it will be in parallel. So another two transistors, that is M7 and M8, it will be in parallel, and the inputs of this M7 and M8 at the gate, it will be C and D. So you can see that in pull down network, M3, M4 are in series, and in pull up, M7 and M8 are in parallel. Those are PMOS transistors. And both the sections in pull down network, you can see in pull down network, this left side section and right side section, it is in parallel. So in pull up network, these two sections will be in series, and obviously the source of the PMOS, it will be at higher potential, that is VDD, and pull up and pull down network will be connected, and from here where I have marked this dot, from here we will get the output Y, and this Y will be equal to AB plus CD whole bar, AB plus CD whole bar. So this is the CMOS structure of this particular expression, Y is equal to AB plus CD whole bar, fine. Now coming to the next example, example 2, let's take Y is equal to A into B plus C whole bar. Suppose that if there is no whole bar, then we will require to connect one more CMOS inverter at the output. So from this expression, you can see that there are three inputs, and these three inputs are A, B, C. So how many transistors we will require if we want to implement this expression using CMOS? 3 NMOS transistors, and corresponding to that 3 PMOS transistors. Now go step by step. B plus C OR operation. So 2 NMOS transistors, it will be in parallel. It will be in parallel. So 2 NMOS transistor, let's say transistor M1 and M2, and the inputs of these two transistors M1 and M2 are B and C, B and C, right? These M1 and M2 transistor, it will be in parallel, and source will be connected to ground. Now this B plus C is multiplied with A, so there is a dot operation. So another NMOS transistor will be required whose input will be A, and both these two sections will be in series because there is a dot operation. So we have drawn the pull down network here that consists of 3 NMOS transistors, M1, M2, let's say this is M3. Now another network which we need to draw, that is the pull up network, that will consist of PMOS. So just opposite will happen. Here M1 and M2 transistor are in parallel, and in pull up network M1 and M2 will be in series. M1 and M2 will be in series. So let's say 2 PMOS transistors, this is let's say M3, and another PMOS, not M3, it's not correct, we can take it as M4. This is M4 transistor. M4 is the PMOS, and another PMOS transistor is M5, right? Now see, since M1 and M2 transistors in pull down network are in parallel and whose inputs are B and C, and corresponding to it, if we draw the pull up network, then transistor M4 and M5 it will be in series. So again we need to redraw it. So M4 and M5 transistor, it will be in series, and the inputs of these two transistors M4 and M5, it will be B and C, right? So here you can see in pull down network, the B and C input transistors and MOS transistors are in parallel, but in pull up network, B and C input PMOS transistors are in series. Fine. Now corresponding to A input NMOS transistor, there will be A input PMOS transistor, and that will be in parallel. So let's take this transistor and just name it M6. So input of M6 is A. Now you can see in pull down network, this A input NMOS transistor is in series with M1 M2. So in pull up network, this A input PMOS transistor will be in parallel. So just connect it in parallel and just join this pull up and pull down network, and of course the source of PMOS transistor, it will be connected to higher potential, and from here we can take the output. That output is Y, and this output will be A into B plus C whole bar. So this is the CMOS implementation of this expression Y is equal to A into B plus C whole bar. Fine. Now coming to the next example, example 3. Let's take Y is equal to A plus B into C plus D whole bar. Now there are 4 inputs A, B, C, D. So there will be 4 NMOS transistors and 4 PMOS transistors. Now you can see this A plus B OR operation. So NMOS transistors will be in parallel. So just take 2 NMOS transistors whose inputs are A and B, and it will be connected in parallel. Let's take, this is M1 and M2 transistor. Similarly C plus D, so we will require 2 more transistors whose inputs are C and D, connected in parallel because of OR operation. And since there is a dot, so these 2 sections will be in series, and source of NMOS, it will be connected to ground. Let's take this transistor M3 and this one is M4. So up to now I have drawn the pull down network. Now to draw the pull up network, you can understand it. Now this since this M1 and M2 transistor corresponding to A and B inputs are in parallel, so in pull up network there will be 2 PMOS transistors corresponding to inputs A and B, but that will be in series. Fine. So this one is, let's take, this is not M3, M5, and input is A, and another PMOS transistor and whose input is B. Let's take this transistor is M6. So you can see that in pull down network In pull down network corresponding to A and B inputs, NMOS transistors are in parallel, but in pull up network corresponding to A and B inputs, PMOS transistor in series. Similarly, corresponding to inputs C and D, NMOS transistors are in parallel. So corresponding to it, we will require two PMOS transistors, and these two PMOS transistors, it will be in series, and inputs are C and D. Fine, let's name it M6. After M6 it is M7 and M8. Now in pull down network, you can see that both the sections are in series. So in pull up network it will be in parallel. So parallel connection will be like this, and the source of the PMOS, it will be at higher potential, that is VDD, and from here, from pull up and pull down network, we can take the output Y, and this output Y, it is equal to A plus B into C plus D whole bar. So this is the CMOS circuit of this particular expression, Y is equal to A plus B into C plus D whole bar. Fine. So basically, up to now I have discussed three examples, three Boolean expressions I have taken, and I have discussed the concept that how we can draw the CMOS circuit of these Boolean expressions. Once you understand that how you draw the CMOS circuit of logic gates, just you have applied those concepts to the Boolean expressions. For example, you had drawn the CMOS structure of two input NAND gate, two input OR gate. Like in NAND gate, Y is equal to A dot B whole bar. So it is a two input NAND gate. So it will require two NMOS transistors and two PMOS transistors. NMOS transistors will be in series for this particular NAND gate, right? And PMOS transistors will be in parallel. Similarly, for NOR gate, the expression is A plus B whole bar. So NMOS transistors will be in, for this NOR gate, NMOS transistors will be in parallel and PMOS transistors will be in series. So just after drawing this NAND and NOR gate, those are the universal gates, you can just apply these concepts to draw the XOR gate, XNOR gate, right, and OR gate, etc. So those are the CMOS implementation of basic gates. Once you understand those concepts, you can apply those concepts to draw the CMOS circuit of different Boolean expressions, like I have discussed three examples in this class. Fine. Now after understanding all these CMOS circuit implementation, you can apply these concepts to draw the various, to draw the CMOS circuits of various combinational and sequential circuits. For example, as far as combinational circuits are concerned, like adder, subtractor, multiplexers, demultiplexer, decoder, encoders, and then further in sequential circuits, you can draw the CMOS implementation, CMOS circuit of different flip-flops like SR flip-flop, D flip-flop, JK and T, further master-slave D flip-flop, master-slave JK flip-flop also. Fine. So these concepts are very important because this CMOS is very important, because at the starting of the class, I have discussed the advantages of CMOS. That advantages are a steady state power dissipation, it is very less, it is negligible, it is very, very less. That is one of the biggest advantage of CMOS. That's why most of the CMOS, most of the ICs are based on CMOS. Also, the noise margin is very good for CMOS because the capability to tolerate the noise, it is very good for CMOS, and it is better for CMOS in comparison with the TTL and ECL logic family. The power consumption is very less in CMOS in comparison with TTL and ECL logic family. That's why we are very much interested in CMOS. And this CMOS logic family, obviously it's a unipolar logic family because we are using NMOS and PMOS, and these are unipolar. But in TTL and ECL, those families are bipolar because TTL and ECL utilizes BJT transistors, NPN and PNP. Fine. So because of its lower power consumption, CMOS is very important. That's why we need to understand how we can implement different logic circuits, different digital circuits using CMOS. Thank you.